Hi there, this is Martin Pawelczyk, and I'm a PhD student at the University of Tübingen, where I work on explainable machine learning. Today, I'll present on the connections between counterfactual explanations and adversarial examples, which is joint work with my colleagues Sharmali Joshi, Chirag Agarwal, Suhini Upadhyay, and Himabindu Lakkaraju from Harvard University. Counterfactual explanations and adversarial examples have emerged as critical research areas for addressing the explainability and robustness goals of machine learning. While counterfactual explanations were developed with the goal of providing reasons to individuals adversely impacted by algorithmic decisions, adversarial examples were designed to expose the vulnerabilities of ML models. In this work, we will make an attempt at formalizing the connections between available counterfactual explanations and adversarial example methods. We will be asking, to what extent do the methods differ? More particularly, can we get guarantees on the difference between these method solutions? To tackle this problem, we focus on popular methods that have been suggested in both literatures, and we start by observing that their objective functions usually look very similar. An example of their similarity can be seen on the right. To allow for an apples-to-apples comparison, we compare gradient-based methods among each other and treat manifold-based methods separately. Manifold-based methods usually use a generative model to compute counterfactual explanations that are on-manifold. All right. We first compare the counterfactual explanations by Wachter with the adversarial examples by Carlini and Wagner. Let's start with our first result. Our first theoretical result says the following. For a linear classifier h of x with logits given by f of x, the difference in p-norm between the counterfactual explanation method by Wachter and the Carlini and Wagner adversarial examples using a loss that was proposed by Carlini and Wagner is bounded by the formula on the bottom. This formula includes both methods' hyperparameters, lambda and c, the weight of the linear model w, the logit score f of x, and the target score s. And the key insight is that the bound is small when the original logit score is close to the target score s, essentially implying that Wachter and Carlini and Wagner are more similar when the input x lies close to the decision boundary. Next, we compare the counterfactual explanations by Wachter with the adversarial examples by Deepfool. And again, for a linear classifier h of x with logits given by f of x, the difference in p-norm between the counterfactual explanation method by Wachter and Deepfool is given by the formula on the bottom, which again depends on the method's hyperparameter lambda, the model weight w, the target score s, and the logit at x. Again, the key insight is that the bound is small when the original logit score f of x is close to the target score s, essentially implying that, again, Wachter and Deepfool are more similar when the input x is close to the decision boundary. This brings us to the evaluation of our theoretical upper bounds using 3 real-world datasets, adult, compass, and German credit. We compare the empirical norm differences, computing by subtracting the adversarial examples from counterfactual explanations, depicted in blue in our box plots, to our theoretical bounds, depicted in orange. For all 3 datasets, we observe that our bounds are never violated, are usually providing very meaningful guarantees, and that the empirical norm differences are very small. Finally, we compare the manifold methods solutions to one another. Here we compare the solutions given by CCHVAE, proposed by Pawelczyk et al., and the solutions by NAE, which was proposed by Zhao et al. We note that essentially both methods use a lower dimensional latent space Z to conduct a random search for adversarial examples and counterfactual explanations, respectively. Assuming that both methods sample from an LP norm ball in the latent space using a L-Lipschitz generative model, we can bound the difference between the counterfactual explanations and the returned adversarial examples by the formula on the bottom again. It says that the LP norm difference is bounded by the sum of the search radiuses multiplied with the decoder's Lipschitz constant. And those quantities, again, can be very easily computed from data. All right. This brings us to the evaluation of our theoretical upper bounds using, again, the same 3 data sets. And again, we compare the empirical norm differences computed by subtracting the adversarial examples from the counterfactual explanations, again depicted in blue, to our theoretical bounds applied by theorem 3 in orange. And what we observe is that for all 3 data sets, our upper bounds are never violated, they provide meaningful guarantees, and that the empirical norm differences are very small. So finally, we are ready to conclude. For popular gradient-based methods, we demonstrated that one can bound the difference in the solutions obtained by adversarial examples and counterfactual explanations. For manifold-based methods, we have demonstrated similar results. Moreover, we see that the empirical norm differences are extremely small for all considered datasets. While counterfactual explanations are meant to explain model predictions, their closeness to adversarial examples raises the questions of whether a trade-off exists in how amenable a model is to generating counterfactual explanations versus its robustness to adversarial examples. And we hope that our formal analysis helps carve out a path for more robust approaches to counterfactual explanations, which is a critical aspect of calibrating trust in an ML.